Hello viewers, welcome again. My name is Geoffrey Omondi. We had started looking at series of probability. In the last class, we talked about introduction and what we call experimental probability. So in this class, we are still going to continue with probability and look at what we are calling probability space and also what we call theoretical probability. So welcome. This is probability. Yes, so we are saying that in the last class, yes, so we looked at the introduction to probability, in which case we were able to discuss and find that probability is simply chance expressed in numerical value. So we say that this is chance expressed in numerical value. And still we were able to look at experimental probability. Now, today I want us to move forward. So today's class, like I've told you, we are going to look at probability space, which is also sometimes called sample space, and sometimes it's also called possibility space. So this is also called possibility space. So apart from probability space, we are also going to look at what we call theoretical probability. So I want us to start straight away with what we call probability space. Now, like I've just mentioned, probability space is also called a sample space and is also called possibility space. Now, it normally refers to the number of total possible outcomes. For example, if a coin is tossed once, then the number of possible outcomes in this place will be either head or tail. Now, when I write H in case of a coin, we are going to be using this severally. This means a head and T means a tail. So the possible outcomes here is either head or tail. Now, this head or tail, this is the total number of outcomes we expect. These are the possible outcomes we expect. These outcomes is what we are referring to as a sample space. That is what we are calling a sample space. Let us look at a situation where two coins, so that was the first situation, two coins are tossed, one after the other. So when two coins are tossed one after the other, what you expect is that the first coin can give you a head and the second coin gives you a tail, or the first coin can give you a tail and the second coin gives you a head, or the first coin can give you a tail and the second coin still gives you a tail, or the first coin can give you a head and the second coin also give you a head. So in this situation, these are the possible outcomes we can get when two coins are tossed one after the other. So this also forms what we call a sample space. So the total possible outcomes that you are likely to get when an event takes place. Let us look at a third scenario. Let us look at a third scenario. A die is cast. A die is cast. Now, when a die is cast, a die normally has 6 faces, and each face is marked with dots. For example, one face is marked with 1 dot, the other face is marked with 2, the third one is marked with 3, the fourth one is marked with 4 dots, the fifth one is marked with 5 dots, and the sixth one is marked with 6 dots. So in that case, when a die is cast, then it means that what we are going to get a face with 1 dot, or a face with 2 dots, or another one with 3 dots, or another one with 4 dots, or one with 5 dots, or another one with 6 dots. Now, these are the possible outcomes. And in this case, this is what we are calling the sample space, or what we also call the probability space. So when you're talking of probability space, basically, this is what you are doing when you're talking of probability space. I want us to move straight away and look at what we are calling theoretical probability. Theoretical probability. Theoretical probability. Now, viewers and learners, we have looked at experimental probability, and now we are looking at theoretical probability. So experimental probability was in our last class, but in this class we are dealing with theoretical probability. So from this, there's something we can see, that the basic differentiation of probability only gives us 2 types of probability. Either you are dealing with experimental probability, or you are dealing with theoretical probability. Now, in experimental probability, we agreed that this is probability based on our past experiences or from an experiment. In other words, if we are completely new in a given situation, we may not find the probability. For example, I gave you an example in the last class. If you are in Kenya now, and you've never been to Kenya, and you've not read anywhere, and you've not done any experiment, it is almost impossible to know whether it will rain in June. But if you have experience of being a Kenyan, and you've also read and you have data to back up, then you can find that it is probable it will rain in June. In such a case, your probability is based on experiment and experience, therefore experimental. Otherwise, there are situations where we don't have to do an experiment to know of a probability. For instance, consider 2 coins are thrown one after the other. So consider 2 coins thrown one after the other. Allow me to clean here. For now, I believe we've all seen what we are supposed to do today. Now we can come up with a small table to show that. So we can say in our table that we can have that, and then we can say this is the first coin, like that. We can also go ahead and say that this is the second coin, like that. We can therefore go ahead like that and say that in the first coin we expect a head and also a tail. Yes, and we can say that in the second coin we also expect a head and also a tail, like that. Yes, and then we can do this that way. So in such a scenario, we are trying to consider this. Now, we are considering 2 coins thrown one after the other. So from this we can say that the first coin can give us a head and the second coin also gives us a head, or the first coin can give us a tail, that, and the second coin also gives us a head, or the first coin can give us a head and the second coin gives us a tail, like that, or the first coin can give us a tail and the second coin gives us a tail as well. So when we look at this, let our interest be here. Let that be our interest. Those of us who can immediately connect will know that what I have surrounded is actually a sample, or what we normally also call probability space. Somebody can see that this is a probability space. Now, I want us to realize that we've come up with this total number of likely outcomes without doing any experiment, because we expect that when we throw a coin, there are only two chances. Either a head or a tail is coming up. And we don't have to do an experiment for this. Now, when we look at that, therefore, we know that this is actually something we can get the answer to. We can get probability without having to do an experiment or have an experience. In such case, that you can have a probability without having to do an experiment is what we are calling theoretical probability. For instance, from above, what is the probability? What is the probability that one will get a head and a tail in that order? So in this situation, we'll now come to our sample space and find that head, tail in that order is only 1. Here it is. So the probability is 1 over the total number of outcome in our sample space is 1, 2, 3, 4. So that probability is a quarter, and we can see that we've done this without having to do an experiment. So when you are able to find a probability without doing an experiment or relying on past experiences, that is what we are calling theoretical probability. That is what we are calling theoretical probability. Now, we can therefore say that in brief, we can write this other side. In brief, therefore, we can give, which we do that. In brief, when you are looking at theoretical probability, the probability of an event occurring, an event is equal to total number of favorable outcomes divided by total number of all outcomes in the sample space. So total number of favorable outcomes divided by the total number of all outcomes. So with that, I want us to take an example. From our books. So our example is from KLB. Probability. So the example I want us to take is this. A basket contains 5 red balls. A basket contains 5 red balls, 4 green balls, and 3 blue balls, balls. If a ball is picked at random, if a ball is picked at random, if a ball is picked at random, find A, the probability of picking a blue ball. The probability of picking a blue ball, and B, find the probability of not picking a red ball. The probability of not picking a red ball. So with that, we can try that together and see what is happening. Now, from this, we have the probability, a basket contains 5 red balls, so we can write that 5 red balls. This basket also contains 4 green balls. This basket also contains 3 blue balls. So the first thing that we have to do here, learners, is that we get the total number of balls. So total number of balls in this case will be 5 plus 4, which is 9. We can say 5 plus 4, which is 9, plus 3, giving us what we call 12 balls. So that is the total number of balls. So find the probability of picking a blue ball. We have said that the probability of any event is given by the number of favorable outcomes over the total number of outcomes. So the outcome that favors us here, in this case, number 1, is blue ball. So we will say, therefore, the probability of a blue ball can be given by the number of blue balls. In this case, there are 3. And the total number of balls we are picking from are 12. So therefore, the probability of picking a blue ball is 3 over 12. Now, we agreed these are fractions, so we can simplify further and say that if you divide 3 by 12, this translates to a quarter. So this becomes the probability of picking a blue ball. Otherwise, for part B, we are asked that find the probability of not picking a red ball. So to pick a red ball, red balls are 5. So not picking a red ball means you are picking from green balls, which are 4, plus you are also picking from blue balls, which are 3. So your favorable outcome here is only 7. The balls you can pick are only 7 because these balls are either green or blue balls, because we are saying we don't want to pick a red ball. So therefore, our probability of not picking a red ball will be the probability of picking all the other balls out of the total number of outcomes, which are 12 balls, like that. Now, we can also say that, or, and I want us to be very keen when we are talking of that or, because it normally helps, especially where you are dealing with a very long question and you are expected to deal a number of things. Or you can say that the probability, now this is correct. we can simply say at this point we are okay, we are also okay. But we can go ahead and redo number B by saying, or the probability of not picking a red ball, can simply be given by the probability of 1, which means picking everything. So this is the probability of everything minus the probability of picking a red ball, minus the probability of picking a red ball. Now, in the first instance now, the probability of picking everything, this is a certain probability. Once you dip your hand in the basket, you must pick a ball. So that is certain. And when we were starting this topic, we say that certain events, their probability is 1. So that probability will be 1. And probability of picking a red ball in this case would be 5 out of 12. So the probability of not picking a red ball can be the certainty of picking everything minus the probability of picking a red ball, giving us 7 over 12 in that case. So normally we can also work with that order. I want us to try and do a few questions in the following exercise. I will leave some questions for you in exercise 13.2, but I want us to try a few of them. So I'll clean here very fast so that we can try a few of those questions. I'll clean here so that we can try a few of those questions. And leave there for you so that you digest as we work on this. So let us look at exercise. Let us look at exercise 13.2. I want us to look at a few questions. Let us start with number 1. If a day is selected at random, if a day is selected at random, what is the probability that it is a Monday? What is the probability that it is a Monday? So the first important thing is to know how many outcomes are in our sample space. So if a day is picked at random, our sample space would include Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, and Sunday. So when we count this, we find 1, 2, 3, 4, 5, 6, 7. So our sample space has 7 items. So we say that simply if you want a probability, you find the number of favorable outcome over the total outcomes, which is actually the total number of outcomes in a sample space, and that gives you the probability. So any day is just one day over the total number of our sample space, which is 7. So this will be the probability that a day selected at random is a Monday. So Monday is one day. The total number of days we are dealing with is 7. So the probability that a day picked is Monday, probability of Monday is actually, let me just write this clearly, probability of Monday is actually 1 out of 7. Probability of Monday is actually 1 out of 7. Let us look at the other one. Let us look at another one, number 2. A letter is selected at random. Selected at random. So a letter is selected at random from English alphabet. From English alphabet. Find the probability that it is a vowel. Find probability that it is a vowel. Now, again in this case, we have to know our sample space. So our sample space, or the total number of outcomes, including both vowels and consonants, have 26 outcomes. In other words, the number of, when you look at the alphabets in English, they are normally 26. So 26 outcomes is what contribute our sample space. But how many letters do we have that represent vowels? So vowels are actually five outcomes. So if you can remember your pre-primary, you can see A, E, O, U. So there are 5 vowels. So our favorable outcomes is the outcomes we want. In this case, it is the vowels. Those are the outcomes we want when we look at the probability, favorable outcomes over total outcomes. So our favorable outcomes, their number is 5 because we need the number for vowels. So therefore, probability of having a vowel would be the possible number of vowels, which is 5, over the total number in all the alphabet, which is a sample space. In this case, 26. So this again becomes our answer for that number 2. Now, very first, we can again look at a third one. We can look at a third one. We can look at a third one. Can look at a third one. Can look at a third one. I want us to look at this one, number 3. So this is number 5 actually. 2 dice are tossed together. 2 dice are tossed together. Find the probability. Find the probability that the sum of the numbers, find the probability that the sum of the numbers showing on their upper face, showing on their upper face is A, 3, B, find the probability that it is 5, and C, find the probability that it is 8. So we want to see the sum, and we want to find the probability that the sum of those will be either 3, 5, or 8. So allow me to clean this so that we are able to see how this is going to happen. Let me also clean this, and to believe we've also seen that. Now the space here is a little bit larger. We can work with this. So when we look at this, we can have die 1, and at the same time we can have die 2. So working with the die 2, we say that a die has 6 faces, so it's either you're going to get face with 1 dot, 2 dots, 3, 4, 5, or 6. Similar, this side we can also get 1, 2, 3, 4, 5, or 6. So with that, we can work that way, work that way, work that way, work that way, and work that way. Still, we can have that, have that, have that, have that, and have that like that. So with this now we can fill. Let me just get a red pen. We can fill. So die 1 when thrown is either going to give you 1, 2, 3, 4, 5, 6. Die 2 will also give you 1, 2. Let me just change this so that we are able to get it perfectly. Die 2 can give us 1, 2, 3, 4, 5, 6. Let's just work with it like that, so that we have this space having nothing. So having drawn that, we can now see the sum. Suppose die 1 gives us 1 and die 2 gives us 1. Our sum will be 1 plus 1, which is 2. Suppose die 1 gives us 2, die 2 gives us 1. Our sum will be 2 plus 1, which is 3. So this will be 3 plus 1, which is 4. 4 plus 1 is 5. 5 plus 1, which is 6. 6 plus 1, which is 7. In this case, we'll have 1 plus 2, which is 3. 2 plus 2, 4. 3 plus 2, 5. 4 plus 2, 6. 5 plus 7. 6 plus 2, 8. The next one will be 1 plus 3, which is 4. And then 2 plus 3, 5. 3 plus 3, 6. 4 plus 3, 7. 5 plus 3, 8. 6 plus 3, there would be 9. And then the next one would be 1 plus 4, which is 5. Then 2 plus 4, which is 6. 3 plus 4, which is 7. 4 plus 4, which is 8. 5 plus 4, which is 9. 6 plus 4, which is 10. 1 plus 5, which is 6. 2 plus 5, 7. 3 plus 5, 8. 4 plus 5, 9. 5 plus 5, 10. 6 plus 5, 11. Then 1 plus 6, 7. 2 plus 6, 8. And then 3 plus 6, 9. 4 plus 6, 10. 5 plus 6, 11. And then 6 plus 6, 12. So we can have that way. Now, we are being told that 2 dice are tossed together. Then we have to find the probability that the sum of the numbers showing on their upper face is 3 in the first instance. So we have to look for where the sums are 3. Now everything inside, this is a sample space like we have agreed. So we are looking for a sum which is 3 here. So that is one of them. That is another one. Do we have any other? No. So in us answering part A, so we are looking at probability where the sum is 3. We say that how many do we have? 1, 2. So we have 2 over. What is the total outcome? Everything here. So that would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36. So that is 2 out of 36. So that becomes the probability of getting a sum of 3. We agreed that when you have a probability in this form, it is not simple fraction. So you can simplify it by dividing 2 by 2, giving us 1 out of 18 in that order. What about number B? Number B can be given by where we want the sum to be 5. So we will surround all situations where our sum is 5. So we have 1, we have 2, we have 3, we have 4. So what is the probability that our sum is 5? We have 1, 2, 3, 4. So in this case, probability that our sum is 5 is actually 4 favorable outcomes over the total number of outcomes here, which is 36. If we simplify this by 4 and 4, we end up with 1 out of 9. 4 divide itself once, 4 divide 36 9 times. Let us see the last part C. Let us see the last part C. We want situations where our sum is 8. So, let me now surround with this. We can have 1. Another situation is this, which is 2. Another situation is this, which is 3. Another situation is this, which is 4. And lastly, we have the last one, 5. So, in other words, we have 5. 1, 2, 3, 4, 5. So, we can say the probability of us having 8 as the sum is actually 5 of the favorable outcomes we are looking of over the total here, which is 36. Now, you realize that this already is its simplest form because we don't have any common divisor of 5 and 36. So that is what we will do to do that question. I want to leave an assignment behind, which I want you to try in exercise 13.2. I want to leave an exercise in exercise 13.2. So in that exercise, this runs from page 246 all the way to page 249. This exercise is in KLB edition, 4th edition. Now, I want you to attempt number 6, number 7, number 8, number 9, number 10, number 11, and number 17. Please do all these. When you do very many questions, it prepares you better because you get more familiar with the workings. Otherwise, for today's class, I want us to stop at that point. My name is Geoffrey Mondi. Have a nice time.